All right, so having a look at number or page 14, we're talking about making predictions. So I'm just going to show you how to crank this out in the calculator. So we go into the regression app. I have some data here. Let me wipe it out. All right, so it takes a sec, but we got to type it in. 74, 66, 81, 52, oops, 73, 63, 52, 45, 62, 46, 60, 46, 38. Oops, got a little off the rails there. So 5, 6, 8, 11, 12, 15, 16, 17, a couple of 18s, a 19, and a couple of 20s. All right, so now that I have it in, I'm going to go to graph. It's asking for the equation of the least squares regression line, which is also known as, well, LSRL, but it's also the line of best fit. All right, so the key word there is linear. All right, so or line, least squares regression line. It's a linear regression model. All right, so I got my graph. Scatter plot doesn't really show much of a pattern, but I go up to regression, select the second one, and at the bottom of the screen here, you can see if I hit the down arrow, it gives me the actual equation. So y hat is equal to 31.934 minus 0.304x. Right? I could also get that if I go into regression. Maybe it's a little nicer here. It also gives us the correlation coefficient R, which is really good. It's all one-stop shopping once you select regression. And it says determine the percent return, right? That's the X value. Right? Given that the percent new, which is the Y value, is 25. So if I scroll down here, you can see predict Y given X or predict X given Y. All right? So I'm going to hit OK on that one, and below that is remove regression. So hit OK on that one, type in the Y that you know, confirm it, and it'll bring you to that point on the graph, but it'll also tell you what it's supposed to be. So the percent return is about 808. And then back into regression, let's figure out Y percent new given X. All right, so that's percent new. Pop in the given value, confirm it, and it's telling us that the Y hat value, which represents percent new along the regression line, is about 4.572. All right. We could also determine outliers and influential points. Generally, the way that works, let me just get rid of this data. It's heartbreaking. Just typed it all in and I wipe it away immediately. All right, but let me get this information in. Simple set of data, 1, 2, 3, 5, 9, 11, and 3, 5, 7, 10, 16, 20. All right. Construct a scatter plot. Well, I got a calculator to do that for me. Go to auto, and it'll recenter it. All right. So I'm gonna take the easy way out here. I'll do a screen grab and I'll just paste it in later. Compute the linear correlation coefficient. So we go into regression, select linear, go back into regression. All right, so correlation coefficient is R. So R is about 0.999. All right, regression equation, Y hat equal to 1.676 plus 1.643x. Determine if there's any outliers. Well, it's a visual thing. All the points are really close to the regression line, so I would say no outliers because there are no striking deviations. From the overall pattern of the data, from the overall pattern of data. All right. Now, that was just really focusing on linear regression. You could also have quadratic, cubic, quartic, exponential, natural log regression. You could even have trig regressions. If you go into this menu here, I'm going to remove the regression, just go back in. You see all the different options: proportional, quadratic, cubic, quartic, powered, etc. These are the ones that we're going to focus on, so we're not going to really depart from that. But looking at this one, that it would, oh, and also this is outdated information. This is in the regression menu. All right, so we have the brownies, the weight, and it's going to create a pattern, so we're going to type that information into our calculators and evaluate it. Home regression, and then clear out the data or overwrite it just by toggling over to data and hitting either OK or enter. I keep saying enter. I mean, it's my first time saying enter this class, but I know that I've been saying it repeatedly over the last couple of weeks. So execute, or exe. All right. So my x1 values would be, and again, this is page 15 for those coming in right now. Let me just put this over here. So your x1 would be the number of brownies. Your y1 would be the weight in pounds. This is fictitious data. I made it up. Right. So yeah, I mean, if a person's eating 99 brownies on a daily basis, then they got bigger things to worry about than computing a regression equation. Oh boy, the Mets just gave up a home run.
Oh, my family's watching it in the other room.
Why
do they have to stress me out?
I just don't understand, like, how the Marlins can
come in, and I know
they're terrible.
I know.
They only wait to play us.
Right. And then, they lose last night. Come on.
Yeah. And now, like, we were lucky to be tied with the Braves, and now we're going to fall behind them.
Exactly. Oh, the agita.
Yes. I remember back in 2006, I was at Game 7 of the NLCS.
Wow.
Yeah, it was great. I saw the Andy Chavez catch pretty close.
Wow.
And then my appendix blew up after the game.
Oh my God.
Yeah, the Mets almost killed me.
Jeez, there you go. Now that you can really say the Mets almost killed you.
Yeah.
And it'd be true.
Yeah, I'm walking out of the stadium. I'm like, oh, I don't feel so good. And then the next day I'm getting my appendix removed.
Oh my God, that's so scary. Yikes.
I mean, it all worked out, so it's a funny story now. But
right, but you can honestly say the Mets almost killed you.
Yep. And I think they're going to try to do it again. I'm not going to let them, though. Not this time.
No, we need the good vibes.
Yeah, and besides, you know what? Maybe it's set up for us to go in and take down the Braves on their home turf or a neutral site, depending on the weather.
Oh.
And then we go into the playoffs as the division winner.
Nice.
Maybe that just sets us right up the rest of the way.
That sets it up. All right. That's what we're going to bank on.
Yep. That's what we're going with.
All right.
Oh, I just realized there's some folks in the waiting room. I'll admit them all. All right. Yeah. So data entry can be, I mean, it's troublesome because you actually have to type in the data and double check it and make sure, because What we've seen so far, with the exception of maybe drawing a graph by hand or something like that, most of the time we're kind of living with technology. And so everything is either going to go right or not right based off of, well, one, whether or not we know the skills using the technology, but that's a distant second to making sure you type the data in correctly, typed it into the calculator correctly. All right, so we double check. I always double check in a way that's different from the way I typed it in. So I typed it in top to bottom, obviously. So I'm gonna check it bottom to top, just so I can kind of get a different perspective. Because, you know, we'd love to have another pair of eyes looking over our work, but, you know, it's not always practical. All right, so the data's in the calculator. And again, we got here by hitting home, then regression. And then we typed in the information into the data menu. I just overwrote the data that was there. If you have data that's already stored in, you go to the column head and you want to remove it. I'm not going to do that because I just typed it all in, but you'd go to the column heading, hit OK, and then clear column. All right, I don't want to do that because that just took a couple seconds to put it in. Now, the possibilities, aside from, and you know, I'll take this as a typo. The other regressions, aside from linear, that can be determined using the graphing calculator, are quadratic, cubic, quartic, exponential, and natural logarithmic. All right, and fortunately, I mean, prerequisites aside, you don't have to be an expert in function related mathematics in order to be able to handle this. All right, the first thing that we do is it says determine using your calculator the best regression model, but I would make a visual determination first. That'll set me on the right path. All right, so determine using your calculator the best regression model, but check the graph to see what kind of pattern you're dealing with. If it looks like most of the points fall in the same straight line, it could be linear. Maybe you have something that's U-shaped, in which case it would be quadratic or parabolic. All right, it could be something that has a dramatic increase early on and then levels. That would be the case of natural logarithmic. It said Zoom cannot detect my microphone. Can you all hear me?
Yeah, we can hear you.
Okay, all right, I just had a moment. You know, it's like one of those moments when you're on the phone with somebody and you're talking and talking and talking, and you realize that you're not talking to anybody anymore because you got disconnected, and then now you wonder, okay, where did I leave off? Turned out it was like 5 minutes ago, you know. So I had that moment just now. Right, but we can look at the graph, and to do that, we toggle up the graph and hit enter. I said enter again, okay, or execute. And you can see we have a scatter plot, and the scatter plot doesn't look like this. It does look somewhat linear, right? But I do see a little bit of, like, I'll just do a quick sketch of it. It kind of looks like it increases, decreases, increases, maybe slows down its rate of increase, but it doesn't actually decrease. Something like that, you know. And so, you know, if you kind of blur your vision, you can convince yourself that it's a linear model. But anytime that there's a little wiggle in it, I'm thinking that it's either going to be cubic or quartic. All right, so the cubic function looks something like this. The quartic function has a kind of a W or an M look to it. And I erased everything else because it's really this one that I'm kind of looking at. It's a little bit askew. You know, if this were the horizontal axis, it would look more like a quartic, but it's not quite there. You know, but it does have that little dip in it. If there's a dip in it, you're probably thinking of some kind of polynomial function. All right. ultimately, it says determine using your calculator best regression model. Why is the one you chose the best? We want the one with the R squared value that's closest to 1. All right. So we could check the graph to kind of streamline our work, but we're looking for R squared value that's closest as an L, closest to 1. All right. So now it's time to get into the computation. Right up on the screen there, at the top says data, graph, stats. Right below that, it says auto, axes, navigate, and regression. All right. We want to go to the one that says regression. All right. And so my suspicion is that it's going to be either linear or quartic, but you might want to test as many things as you can. All right. So you go to regression. And that's kind of aggravating, I would think, because to get into this entire menu to begin with, you had to hit regression. Now you're hitting regression again. All right. So that's kind of a step-by-step. But then you see the different models that you could have. At the top, it says model linear, and it actually gives us the R squared value for the linear model. So I can make a note of that. The R squared is about 0.972. All right, but I want to try a different model. So I hit OK, and you see here we have proportional. Well, proportional is really just a multiplier of X giving you Y. All right, but more simply, you're looking at a line that goes through the origin. All right, so if you don't have any reason to think that there's a line going through the origin, then I wouldn't mess with the proportional. But quadratic, I don't know, it seems like it might fit a little bit better, but I'm not really 100% sure. So you select the model that you're interested in, and then go back to regression, and it'll tell you the equation, the regression equation following that model, and then it'll give you the R squared value. Right now, we're only interested in the R squared. All right, so quadratic, the R squared is about 0.976. All right, the closer you are to 1, the closer you are to perfection, a perfect fit of curve to point. This one's better than linear, right? Because it's a tighter fit. All right, but I want to get greedy here. So I'll select model, go down to cubic, and you see if you go down the line here, you see a ton of them. All right, but cubic is next on the list. It'll give you the graph. Doesn't look much different. Go back to regression. So you're just going back and forth between graph and regression. All right. Another person coming in here. But you can see here, in this equation, you see how it's X with a little caret then a 3? That's power of 3. So it's a cubic function. And the only reason I bring that up is because the R squared value for cubic is exactly the same. Well, not exactly, but it rounds to be exactly the same, if I could say that, to 0.976. So it's not any better than the quadratic. If there's a tie, you go with the simpler function. All right. A tie goes to the simpler function. So I would eliminate linear. So I'm just going to put a strike through and cubic, because even though quadratic and cubic have the same R squared value, quadratic is a simpler function. I'd rather work with that. All right. But we have more options here. So I'm going to go to quartic, also known as a 4th degree polynomial. But that just basically means that the highest power is equal to 4, as opposed to in this case where we have the highest power equal to 3. So model quartic. It looks like it fits a little bit better, but let the data tell us whether that's true or not. You go back to regression. Now I'm looking at 0.993 as my R squared value. All right. So we checked quadratic, cubic, quartic. I suspected that it was quartic, and that's about 99%. I mean, that's pretty good. But just to be thorough, I'm going to check exponential, and I'm going to check the natural log. All right, so we go to model, logarithmic. Now it says logarithmic in here. We should do exponential first, but just to talk about logarithmic, I say natural log here. They just say logarithmic. If you look in the notation, it says a times b ln x. That ln stands for natural log. All right, so that notation ln means natural log. All right, so don't get thrown off by the fact that this is logarithmic. It is still natural logarithmic, or a natural log. And it's understood that you may not have too much experience with logs. Fortunately, we're not going to do anything by hand involving logs. It's all going to be calculator work, so you'll be in pretty good shape there. I'll just walk you through it. All right, so but I'm going to look at exponential first. So this is what an exponential curve looks like, or at least a portion of it. And you'll notice that only the relevant part of the graph is showing up here. So that's good news, because in most cases, when you're dealing with creating a graph by hand or using technology, most of the time you have to account for the window that you use. How far left, how far right, how far down, how far up. The NumWorks calculator takes care of that for you. So I go back into regression. Here's my exponential model, which it has an R squared of 0.934. And then I'm going to do the same thing, but now with the logarithmic, right? And for that one, we're looking at an R squared value of 0.939. All right. Now, very important in statistics, context overrides computation. So I dropped a few gems here. So let me jot these things down. First off, a tie goes to the simpler function. All right, so if we were only testing to see if it was quadratic or cubic, they both had a 0.976. That's a tie. Those two values are the same. You choose the simpler function, which would be quadratic. All right, but also, so that's one little note. Another one is context overrides computation. This is where I find out if I spelled overrides correct or not. I really feel like there's only one R, but no, it's two R's. I mean, it seems like it's a compound word, so it makes sense that it would have two R's. It's one of those words that when you write it, it feels like it's not correct, but fortunately, my instincts carried me very well here. All right. So context overrides computation. So if you look at a scenario and say, you know what, I think it makes more sense for it to be an exponential function, then you could make that call, right? Even though it doesn't have as good of an R squared value, right? So based off of what we have here, by the numbers, quartic is the best option. All right. Everything else would be out. But I will say that a good alternative would be the natural log function. I'll explain why in a sec. All right. So I'm not going to put a strike through on that one because that's a good alternative. In fact, some people may think the quartic is the alternative and the natural log is the primary. That's the one you should go with. What I'm saying here is if you selected either of these, this one or this one, you would be right depending on your justification. All right. The thing about a natural log function or any other logarithmic function, just making a little note here, is that unless there's a transformation involved, you're starting off with something that has a very dramatic increase early on, and then it levels off. All right, so this is typically what a logarithmic function would look like. All right, now if I compare that to my graph, it kind of has the flow of something that's leveling off. All right, so you could make the case based off the context that, I mean, really, we're talking about number of brownies that you're eating on a daily basis and the weight of a person in pounds. I mean, eventually the weight's going to level off regardless of how many brownies you eat. All right, you're going to just, whatever your maximum weight is going to be, eventually you'll be more brownie than human, so it's just one of those things, like you can't get past the natural barrier. All right, so if you're making a case for that, you could say natural logarithmic, even though the r-squared value is not as good. All right, but if we're going by the numbers, what we would say is that the quartic is the best bet. So all of this was to address part A. Now it's like, oh, okay, so we'll be at this for another half an hour while we answer parts B and C. They're much quicker now, because now that we know what the function is, we can work with that function. All right, so for B, determine the equation of best fit. We already have that. All right, we just got to go into the regression and grab it. So we want quartic, because that's what we deem to be the winner. So you select quartic and then go into regression again. So it's really just going back and forth into regression. And then you just jot down this equation here. All right. You may consider rounding it just because the numbers are a little crazy, but you could also technically write the entire thing if you want. So the equation of best fit, we say y equals, now I'm looking at this, I see scientific notation there. See that E -5, that capital E, that's scientific notation. So we would just take the first few decimal places, -2.6, well, really 8, times 10 to the -5th power. All right, multiplied by x to the 4th. All right, so that's what that E -5 means. It's accounting for the scientific notation. All right, so I rounded to the first few decimal places, and then from there, I'm just grabbing the times 10 to the -5th power. All right, so always check at the end of a constant, especially when it's real data analysis, check for any scientific notation. So then I would continue my equation. So plus 0.00591 x to the 3rd. So that little caret symbol means. Then minus 0.440 x squared plus 14.975 x, and then plus 0.0711. Yeah, it's a plus. So this whole thing is your equation. Normally with a polynomial, you write it all in one line, but this is a lot, so it's all right to write it stacked like this. And besides, it really highlights what the coefficients are. So that really is pretty useful. All right. So you see at the bottom, you have something called residual plot. We'll come back to that in a little bit. I might actually use this example to kind of prove a point, but it's a pretty important concept. All right. You could also, I'll just show you real quick, just navigating around here, you can go into stats and you can get things like the mean, the standard deviation, variance for each variable. All right. And it'll also give the appropriate regression equation. What it does is it gives you the model, and then it gives you all the coefficients right after that. So that's kind of useful. If you have trouble scrolling along that line that I showed you a couple minutes ago, here you have all the coefficients all in one shot. So that's kind of nice. All right. Then the other thing is, well, if we're going to address part C, we would want to have a method by which we can compute those values. Or in this case, it's just a one value. So just going back to graph, you could do a couple of things. There's a couple options. One would be to go to navigate and just kind of scroll around until you come up with something that you think would allow you to at least come up with a reasonable approximation of the answer. So they're saying, what weight would you expect a person who eats 100 brownies per day to be? So what that's saying is when X is equal to 100, what is Y? All right. So you could do that, and it would give you an estimate, which is, not ideal, but it's manageable. The other thing that you could do is go into the grapher. Yeah, there's a way to do it with the solver also. Oh, hold on. I can jam myself up here. Maybe I'll do it with the solver. No, that's only going to work with linear systems. So, all right. Trying to think of the easiest way to do it, because you really, I mean, if you want, you go right into the home screen and go to calculate and just type in the 100 for X. So let me show you that way first, because that's the most straightforward approach to doing it. But then I'll show you another way. I also I do have to take attendance, so I'll do that in a minute also. So negative 2.68. All right, we want to go times 10 to the negative fifth power. So times, there's what you call it, the same kind of notation here for scientific notation. You could work with that. See right at the bottom, right next to ANS, it says times 10 raised to the X power. So you could select that and put in -5, or you could use, I'll show you real quick, is X to the N key. I'm sorry, X to the Y key, type in the 10 and then hit that and type in a -5. Either way, this one is just the one at the bottom here is just a shortcut for it. I accidentally hit it twice. So we're going to take that and multiply it by 100 raised to the fourth power. So that's again the X to the Y key, just like, honestly, just like you would find on a scientific calculator. All right, so plus 0.00591 multiplied by 100 cubed minus 0.440 times 100 squared plus 14.975 times 100 plus 0.0711. Right, so I mean, it's a little mind bendy when you have to type it all in that way, but you hit OK, hit enter, and it'll give you the value. So what you're actually computing here is Y of 100. All right, that's function notation, not Y times 100. If you think back to f of X, if you remember that, it's the same idea. This gives a value of 325.571, 327.571. All right, and so that would be, it's the weight in pounds. So little notation at the end, LB, LBS. And now you have what we call a prediction. All right, so there is a way, like I said, to make a predictive value, but I encourage you, if you haven't already done so, to just kind of click around and see what you can find in the calculator, because some of the things you wouldn't expect the calculator to do, it actually does fairly well. A good place to start would be right next to the backspace button, the little toolbox. you have a whole bunch of things that you can do here. All right, so you just look at it. If you're looking for anything funky, this is probably where you're going to find it. And we'll come into this menu a fair amount when we get into the second unit and talk about probability. So so pretty useful there. All right, but let me pause for a second and take attendance real quick. So let me pause the video. Actually, no. Yeah. All right. So you can, if you're in the regression menu, so again, you have all your data and you go into regression, you could just kind of toggle back and forth, not necessarily along the points, but along the actual curve itself. By hitting up and down arrow, it takes you back and forth between point and curve. So if I have that, you see that little crosshair there? If I have it like that, then when I go left and right, it'll take me just to the points. All right. But if I hit the up or down arrow, it puts me on the curve itself. And it's a good way to get a quick estimation of what the appropriate value would be. All right. So it kind of hops over 100, but you know that the value is going to be somewhere in the neighborhood of 324, 318, something in that neighborhood. Right. So you can get a ballpark estimate that way, and it's pretty reasonable. Yeah, because we could do all all sorts of different approaches, but like when you're looking at an equation that's this nasty, sometimes it's the estimation is really all you need. There's also, if you go into let me go back because I'm kind of hopping around here. If you go into the regression menu and hit enter, if you want precision but you want the calculator to do it for you, then you go down. We're in that's the quartic model right here, this messy equation. This is my R squared. Then it has options to predict Y given X, or predict X given a find X given a predicted Y. All right. So what we just did in part C was predicting a Y given an X. So if I hit OK on that, I could just type in the number that I want and hit confirm, and it'll give us something a little bit more precise. Now, because I work with rounded values when we did it in the home screen, we got 327.571. Right? It might have been an unacceptable amount of rounding. I'm not really sure, but honestly, if you're in the neighborhood of the correct answer, I mean, it's a 6-pound difference. You're already in the neighborhood of the 320s. So it's different if you're talking about, let's say, the weight of a 1-year-old. Being off by 6 pounds is very significant, but as a percent of the whole, 321 versus 327 isn't really that much of a difference. All right. So again, if you want to do it in the calculator, so in the NumWorks, you're going to go to regression. And then you're going to go down to predict Y given X. All right. So we have 3 different ways to come up with our answer. And, you think about like a multiple choice question. I'm going to give you 4 choices, and one of them is going to be way off. Something that's absurd, like any other multiple choice question. One where it's like, okay, well, it's not that one. Then there's going to be something in the 320s. And then there's going to be something maybe in the high 200s, and then maybe something like 150. And so it's not going to be a matter of choose the best one that fits 327, 321, or the estimate that we came up with, which I think was a 324, if I'm not mistaken. But it's going to be something that you could easily lock onto. I just wanted to show you the way to get a reasonable estimate without having to go too crazy looking for precision. All right, because if you're in the neighborhood, most of the time you're going to be okay. And besides, if you had elected to go with a natural logarithmic here, you might have gotten something completely different. So if I go to regression, and I believe, for example, in this case, that it's a logarithmic, that's what the model would look like. If you want to go back to the original setup, you can select auto, and it'll bring you back to what the calculator thinks is the best window to view, right? And then you can navigate from there. But if I wanted to do just a prediction with the natural logarithmic, same deal. You go down to predict y given x, type in what we think, 100 in this case, and it'll tell us what it thinks the value is. Of course, I must have hit something weird. Predict y given x, 100, confirm. Oh yeah, it was there the whole time. I just, for some reason, I didn't trust myself. That y with a little hat over it, it gives it to us as a kind of a weird representation. That y hat stands for predicted model, right? Technically, we should write y hat equals, but if we're just typing in an equation, it's kind of confusing that way. So we just, we can kind of go either way as long as you know it's a predictive model. But this says it should be around 308.0274-ish. So if you had selected the natural logarithmic model, that's what you might have come up with. All right. So personally, I would always try to see if I can make a linear model work. All right. Because you could have really complicated functions that better fit the data. But the problem with that is those really complicated functions are really complicated. All right. So if you can get away with using a simpler function, then that would be the way to go. So with that in mind, we talk about something called a residual. All right. So let me go back. I said I'd use this example. And I'll take you through the next couple of pages also, but it's a really good example to think about, because let's say I wanted to use a linear regression. So I go into model and I wanted to keep it as simple as possible. The linear, well, actually the simplest would be proportional, but the simplest from our list of things that are useful, linear. All right. And again, if you're not sure about the window, go to auto and it'll reset. Now you may look at this and say, I don't see anything wrong with the linear model. Right. So how can you justify using a linear model when maybe somebody else is saying it's got to be quartic or natural log? I see a question.
That was going to be my question. What if someone uses something different, and then wouldn't it give different values for different students?
Yeah, exactly. It would give different values, but if you could justify your decision with appropriate technique, then you're right also. All right. So we could be looking at 4 or 5 different correct answers for this particular problem. And so the burden is on me to go through your work and see, oh, yes, you were right. Even though you didn't choose what I chose, you're still good. All right. So how can we justify the linear? We go back into regression and you see something called a residual plot. All right. The residual plot is very important. And you can see, like on the next page, next set of pages, there's like all explanations of how you come up with residuals and things like that. But I'm just going to hit OK on the residual plot. And what that gives us, well, the simplistic explanation is it's a plot of the residual values, all right, which doesn't really help. But if I tell you that a residual is the difference, so on the next page, residual equals y minus y hat, notation, wonderful. But what that means is it's the difference. My battery's going low, so between the observed and the predicted values. See if I can get this on a charger quick before it dies on me completely. Okay, start one. All right, time out for a sec. I'll be right back. I'm looking for that little dongle jammy to charge my Apple Pencil. I think I found it. All right. At least while I'm blabbing away over here, I can do something productive. Aside from, teaching really important mathematics, but you get the idea. All right, so let that charge for a couple minutes. The difference between observed and predicted values. All right, so we would want these these residuals naturally to be as small as possible. All right, because when I tell you that there's a difference between observed and predicted, you look at it and say, okay, well, what is observed? Observed is what happened. Predicted is what your equation says should happen. So the smaller that difference is, the closer your prediction is to what actually happened. That's a measure of accuracy, right? So we want this to be as small as possible. Now that it's charging, I can't actually write with it. Yep, technology, disconnect. All right, so I want that difference to be as small as possible. I'll settle for a scattered arrangement in the residual plot. All right, so if I don't see, when I create a residual plot for a linear model, if I don't see a pattern in that residual plot, that means that the linear model is appropriate for the data. All right, so ideally we'd have kind of a combo platter where the differences between those points on the x-axis would be really small. So they'd be really close to the x-axis. And depending on how you zoom in and you set your window, it may not seem very close, but maybe it's closer than it actually seems. All right, but what we want is a scattered arrangement of points around that x-axis. That allows for a linear model to be appropriate. All right, so scattered arrangement. Apologize for the handwriting. I'm writing with my finger right now because my Apple Pencil died. Scattered arrangement around the x-axis. Means the linear model is appropriate. All right. That's really what all this is getting at. I mean, you can compute the residuals and plot them individually, which we tend to not really want to get into. Right? If anything, I'll ask you to just compute one or two residuals, maybe fill out a table or something. But fortunately, if I just toggle along here, it gives me the residual for every single x value. So if you did need to make a graph, you can get it all from right here. All right. In the past, I would have students make the graphs on a test, but I think going forward, I mean, the technology does such a wonderful job. I don't want to waste that. So if anything, I'll have you just state the residuals for certain x values. All right, I'll show you what that looks like in a minute. But I'm looking at this residual plot and I'm not seeing any discernible pattern. So that tells me that the linear model is appropriate. Now, when we say it is appropriate, we get into kind of like the law of double negations, it's like a logical thing where I'm not really saying it's appropriate. I'm just saying it's not inappropriate. All right. So, but when you say something is not inappropriate, you're saying it's appropriate. So it's kind of like, well, is it the best option? Maybe, maybe not. This is saying that if you did choose a linear regression, you would not be wrong. All right. So even for that example, and this is where the data came from, even from this really complicated data set with funky numbers, depending on the Cordic regression. You look at it, you see an R-squared value of 0.972. That's not bad. That's pretty close to 1. Yeah, Cordic is closer, but the residual plot tells me that it's okay to use a linear regression. So I could have used that information and decided, you know what, I'm going to go with a linear regression. But again, just like we were saying before, somebody else might say, well, contextually, linear doesn't seem to make sense, because if you eat 1,000 brownies, then are you going to be like 15,000 pounds? Probably not. There should be a leveling off factor. You know, so you get into like that gray area, but technically by the numbers, you could go with linear, right? So it kind of opens the door for that. All right. So this is really more of just notes on it. And the next page is the same deal. Let me just get rid of that stray mark. You can read through that. It's pretty basic stuff, with the exception of the concept of an outlier. All right. A point that is an outlier is going to have a deviation from the overall trend of the data, right? So, and it's usually a noticeable one, right? You'll have a point that's just kind of out in the middle of nowhere, and that would be an outlier, right? So, I'll take you through an example that shows an outlier in action on page 18. The data, you know, it's another one of those deals where I got to type the data in, and I do have to reconnect my Apple Pencil. So I'm going to just stop the share for a sec. Let me stop the recording also for a sec. Oops. Always entertaining. So just keep, you can either keep hitting the up arrow until you get out of the plot, or you just hit the back arrow a couple times and it'll take you where you need to go. So in data, I need to get rid of all this information and replace it with this new information. And if I'm not mistaken, there's more information that I already have plugged in than what I will be plugging in. So I'm going to go right up to X1, hit OK, and go to clear column, confirm it. And then you see the Y1 values are all grayed out now, because if you don't have a corresponding pair, so for every X1 you have a Y1, it won't do anything with that information, right? So it'll hold it, but it won't actually plot anything. So I want to clear this out too. So clear them both out. Confirm. You know, that confirm option seems like an unnecessary extra step until you get to a point where you're like, oh no, I didn't mean to clear out that data. Then it's like, oh, okay. Fortunately, it has a confirm option. So that's good news, because really undo with handheld calculators is not as easy as it may seem to program in. All right. So typing in my X values first, then my Y values. Now you'll notice for my X1 values, I'm going down the line here, and most of the values are single digits until I get to this 20. 20 seems to be coming out of nowhere. So I'm going to hold on to that in my mind for a couple minutes and then see later on if that maybe is an outlier. All right, so let me just get the rest of the data points in. 42, 39, 25, 70, 40, 15, 45, and 52. All right. So I have my data in. It says draw a scatter plot. All right. I'm going to say observe the scatter plot. So it's a typo for somebody. All right. Typo being the word of the day. Typo, T-Y-P-O, because I have made a few of them and I feel like it's just naturally begging to be the word of the day. All right. Label and scale the axes. Well, let's not worry about that. Is there a pattern? Does the data appear to be positively correlated, negatively, or neither? All right, so I'm going to go into my graph, and now I have a scatter plot. All right, so I'm looking at points, and like taking a class that's digital in nature. So if I asked you to make a scatter plot, I mean, personally, if I were you, I would do it like this and then take a screenshot and submit that. Like I'm not going to make you do something by hand just for the sake of doing it by hand. I mean, if we were in a classroom together, that would be a different story, but that's not the case. All right. So in fact, just for the sake of having decent notes here, I'll just pop it right in. Copy, done. I'll save it to photos. Paste it in, and there we go. We have a nice scatter plot. All right. So something to at least point at. Now, looking at specifically this point and this point, I ask myself, if I could remove those points, would I have a noticeable pattern? All right. So what I would say is that there is a pattern. Right, it appears to be a positive linear, possibly, or even I'm looking at something like this, maybe a cubic. Relationship. Aside from those 2 points, all right, those 2 points I highlighted in yellow, though they seem to be, we'll call them outliers, but they seem to be a little out of whack. All right, just to keep it simple. All right, so what we're going to do is we're going to figure out whether or not they're outliers. All right, so is there a pattern, positive, linear, or cubic relationship? The fact that I said positive in there covers the second part of the question. Now, the correlation coefficient R, all right, so we're looking at, there should be the linear correlation coefficient R. So typos galore. Honestly, that I believe is a legacy typo. That one's been there since the beginning. And it's been on my list of typos to fix, and I just never got around to it, I guess. All right, but we're going to go on up to regression. We're going to select linear. And yeah, that does not look like it fits the data very well. However, they didn't really ask us that. They just asked us to determine what the R value is. The linear correlation coefficient R. If you go into regression, you see you have only the R squared value. That's kind of annoying because you'd have to take the square root of that to figure out the R value. So then you'd have to write out the decimal, go to the home screen. A better option would be to go to, let me just back it up here, go to stats. All right, so go to stats. If you go into that menu and scroll down, so you have your 2 columns of information here. After a while, you see that the only information that you have is related to the Y's, the Y1. All right, you'll see it has a coefficient A, coefficient B, correlation coefficient. That's the R value. So you can get it right from there. All right, so go to correlation coefficient. And the good thing about, or one of the good things about NumWorks is that it gives you the little notation right there too. It's saying R. Well, I happen to be looking for R, so that works out nicely. It also gives you the R squared value, but that's not what we were asked for here. So 0.444 we'll say. Regression equation, it gave us that too, right? So we have Y equals AX plus B. And right below that, it tells us the A and it tells us the B. So we'll say y equals 1.546 x plus 25.845. All right. So now I have the regression equation. And if I need to make a prediction, I can do that too. So outliers are points that are off of the ordinary path, or they say off the beaten path. But really, it's just you have a line that would fit the data if not for these 2 points. All right. Because those 2 points are in the graph, you have a line that looks something like this, which doesn't look like it fits the data much at all. What I want to see is what would happen if I took this point out. All right. And then what would happen if I took that point out? So these are points to be removed so that we can recompute the correlation coefficient. All right. Outliers in general are any points that are off of the distribution. So most of the points are kind of falling in line. Those are the 2 that are not there, not in lockstep with everything else. Influential points are outliers in the x direction. And all that means is that you have a point that's not just an outlier because it's above the data points. It's an outlier because it's further to the right than the data points, or to the left, but it's a horizontal displacement rather than a vertical displacement. So this one would just be an outlier. This one would be an influential point. All right. So what we do, the way we handle this, is by removing the data point from the set, whatever we suspect. That first point, the one on the top end, that's 8,70. And this point here is 20,40. All right. I suspected there was something off with the 2040 when I was typing the data in. I didn't really consider the 870. All right. But what we'll do is identify these possible outlier, 870, possible influential point at 2040. Went a little crazy with the abbreviations here. Hold on, let me fix that. So possible influential point at 2040. All right. So the way we determine if it actually is an influential point is by removing it from the data set and then recomputing to see if there was a substantial change in the linear regression equation. So, overshot the Mac. So I go up to my data and I can do this one of 2 ways. One way, my preferred way, is to copy my information over into X2, Y2 so that I don't lose my original data set. All right. So if I hit OK on X2, you have an option to fill with formula. And that formula, so let me just make a note, go to X2, hit OK, and select fill with formula. All right. And then select empty. All right. Sometimes they have options in there for you that you may be looking to use. You go down the line in the hopes that maybe exactly what you're looking for is there, but it doesn't always end up being the case. So I'm going to hit OK. It says X2. I want X2 to be the same as X1. So X2 is what they have here. I want to type in, well, a capital X. You see how if I just hit X, it brings up a lowercase x. So the X button right above the 2 to get it to be capital, I have to hit Shift Alpha 2. Okay, let me do that again. Shift Alpha 2. One more time. There we go. My fat fingers weren't really locking in the way I would have liked it. But that would be X. I type in a 1. And when I hit OK, it will have replaced all the empty X2 column with everything that was in X1. All right. You can also retype it, and you could also just go and delete from the original table. But this is a little bit more efficient. I don't want to say user friendly because that's not fair, because it's not. All right. But it's a little bit more efficient because you could replicate your data and then just remove from one of the data sets the thing that you want to remove. So if I hit OK on Y2, fill with a formula, empty, I want this to be the same as Y1. So Shift Alpha 3, and then type in a 1. So X2 is equal to X1, and we want Y2 to be equal to Y1. And when you hit OK, it populates all those values too. All right, so it's an exact duplication of what we had in X2, Y2. And the reason I want that, if I can get to the right spot here, the reason I want that is because when I remove my 2040 here, so I'm going to hit the clear button, I have to delete the thing that goes along with it. I don't want to lose my original data set. All right, that's the benefit of doing it this way. All right, so I'm going to also remove the 870 in a sec, but I wanted to just look at what would happen with the graph if I had the 240 omitted. All right, so go back to graph. And now you see that there are blue points and there are red points. All right, well, red point. All right, because the blue points are overlapping the red points. All right, so, but what I can do is I can go into regression. Now I have two options here, X1, Y1, X2, Y2. So under X2, Y2, same thing, linear. Now you can see a comparison between the two graphs. All right. So what I said before was, if we took one or both of these points out, I could get the graph to look something like this. And that's exactly what happened when I took out the 2040. All right. So we remove 2040. And now you have a much better fit. All right. So it's a much better fit. All right. So that in and of itself is worthwhile because you're looking at just appearance wise a line that better fits the data. But maybe you don't believe it because we know what the R value was for the original line. Now what I can do is go back into regression and look at my R squared value. But again, if I want to look at the R, I got to go into stats. But you could do a comparison of R squared values also. Whichever one is closest to 1 is the one that you want. All right. But if you want to see the R's, you go into stats, go down the line till you find the one that says R, go across the line, and you see that the 0.444 just became a 0.785. Right. That's much better. All right. So I'm just going to get a little sneaky here. Just move this over a little bit. And then maybe do a little resize. All right, so R is now, so I'll say the new R is about 0.785. All right, so, I mean, that's pretty good justification for assuming that that was an influential point. All right, an influential point will have a substantial, significant impact on the R value or even the R squared values. But now let me just do, and this will be the last thing that we do, at least in this area, because I got to talk to you about the practice test and stuff. So let me do the same thing, but this time I'm going to remove the 870 instead of the 2040. All right. So what I'll do is here in this field, I'll just replace the 870 with the 2040. That's basically what you would get if you pulled out the 870 instead of the 2040. All right, then we go to the graph. Not much of a difference, all right, in terms of just the appearance of it. The red is what you would have had if you left all the data points in. The blue is what you have just by removing the 870, that point where the crosshair is at the top. It's a minuscule impact on the graph. All right. So that's the reason why we call it influential. Sorry. It's not over yet, but the Mets just got on the board.
Woohoo! Let's hope they could keep it.
Yeah,
Keep it
exactly.
going.
2-run shot by Escobar.
Wow.
But now we're down. Well, we were down 4-0. So, but it's bottom 7. So this is nail biting time, I think.
Typical.
And Aaron Judge just hit a 61.
Oh,
Aaron
wow.
just did it.
Yeah,
Nice.
Yeah.
and no one caught it.
Hey, it took him a while to get there. Like that 61st one took what, like over a week, but I'm glad to see he got it. He seems like a good guy.
Yeah, he is. He seems like it. So
Yeah, it's kind of, I always look for something to dislike in Yankees, and it's probably more frustrating when I can't find something to dislike.
yeah, exactly. That's all right.
Yeah, let him have it. So construct a residual plot and discuss its implications. That's what I was saying before, that I'm not going to ask you to do that, but we can look at the residual plot. Now, I'm going to go back to the original data set here, and let me get rid of, I'm actually just going to go in here and you know what? I think probably the best option, if you want to turn a data set off, the best option is to put a value in one row, but not a value in the corresponding other row. Right. So you kind of clear one of them out, and it'll gray it out so that you don't have to see it. I mean, there's other ways to do it, but that's probably the most convenient way. Right. So what I would do here is go into regression and go down to residual plot. And it actually brings me into another graph, completely different graph. But it's pretty clear what the residual plot would be in terms of the points. Now, if you look at it and compare it to the original scatter plot, you kind of see that it has a similar structure to it. What actually happens is you take a scatter plot, and let me just do this real quick. Copy, I'll bring it down. And this is the number one reason why I'm not going to ask you to make a residual plot, because if you have the line of best fit on a regular scatter plot, but then you rotate it or turn your head, leave the paper the way it is, but then turn your head, what you're going to end up with is the same distribution of the residual plot. All right. So it's nice to be able to construct these things, but if you take your scatter plot with the line of best fit on it and just turn it so that the line itself is horizontal, you have your residual plot. All right. And so outliers really should become pretty obvious. So this is my residual plot. I know it's not pretty, but this point here is very far above the x-axis. So that would make it an outlier. All right. This point, the influential one, wasn't really that far away vertically, but it is far away horizontally. All right. Most of the points are over here. You have that, oh, that jumped on me. The extra point over here, that's kind of like in the middle of no man's land. All right. So that's really all there is to it when it comes to evaluating a residual plot. Yeah, just looking to see if there's any striking deviations from the overall pattern of the distribution. Now, the implication that you're going to run into here is that a linear regression may not be the most appropriate. And the reason for that is because, pause for dramatic effect, I'm seeing a pattern in the distribution of the residual plot, right? So there appears to be a pattern. The residual plot shows a pattern. And it really doesn't matter what the pattern is. Any pattern whatsoever will indicate that whatever model you're looking at, in most cases for us it's linear, is not going to be appropriate, that some other type of function would be the most appropriate, right? But sometimes, even though it's not the most appropriate, sometimes, you know, you sacrifice a little bit of accuracy for efficiency. So it's basically the case that if you know that you're going to lose a little bit of accuracy, but you'll be able to get the job done much quicker, you know, it's almost a definition of cutting corners, but it's enough to get a good idea of what's going on in the data without having to get bogged down with all the data analysis, right? Because when you go too much by the numbers, you end up really doing just that, getting bogged down, right? For G, we actually already really did this. So, you know what? I'm in a typo frame of mind right now. So let's get rid of those. I kind of jumped the gun on the previous page, but hey, it works. But the last little bit here, a new job applicant scores a 9 on the aptitude test. All right, it's very easy to forget what you're doing when you're answering a question. And if memory serves, I didn't even read the preamble here. An employer gives an aptitude test to his employees and compares it with their productivity at work. The results are given. So X is your aptitude score and Y is your productivity. So contextually, you may say, all right, well, it makes sense that if your aptitude is higher, then your productivity might be higher. But anybody could argue the reverse of that and say, just because your aptitude is high doesn't mean that you're like a hard worker. You know, you could have all the intellect or even the background knowledge in the world, but if you're not motivated to do the work, why would your productivity be good? You know, so you can go either way with that. But what they're saying is using this information, knowing that the aptitude score is 9. So if X is equal to 9, what is Y? Right. So it says use the regression equation without the influential point. All right. So that's the one that doesn't have the 2040 in it. All right. So I got to go back to my data. And I want the 870 back, but I don't want the 2040. And now I can delete this 1 here so that it'll actually show up. All right. So then I go into my graph. We could do the regression again. Y1, linear, it shows up. If you want to actually use the equation under regression, you can go in here and pull the equation out and make a substitution. That's perfectly fine. Or you can go to predict Y given X, type in this case, they want a 9, go to confirm, and it'll tell you the value at the bottom. So when X is 9, Y is equal to, oh geez, I need a new prescription here. 48.187, I think. Yeah. All right. So that's the productivity level. Right? And they didn't give us units, meaningful units for that. So this is what we would expect for an aptitude level of 9. All right, a productivity level of 48.187. All right. So yeah, that's really all there is to it. I know it's a lot, so I'm kind of being facetious when I say that's all there is to it, because that's a lot of stuff. All right, but it's all calculator intensive, and if you play around with the calculator, and again, numworks.com, handhelds are nice, but I'm using an app right now. That should tell you. You could get the app on your phone if you have a tablet, or you could just go to the numworks website and go to simulator. All right, and hopefully you've kind of been aware of that this whole time, because that's what I have been emphasizing. All right, so that's the unit, but I wanted to take you to the practice test real quick, and it has everything to do with the fact that Brightspace is oh, hold on. Let me do this real quick. Stop the recording.